All right, excellent. So everything has disappeared. I'm not sure why. I can never figure this out. It's the same reason I can't figure out my email. Okay. What I've lost is, okay, well, all right. You can hear me and see the slide, is that correct?
Yes.
Excellent, okay. Okay, I mean, it's all too much for me. So, Dirichlet series of integers with missing digits, which is what I've been talking about every 2 weeks or so for a couple of weeks. And somehow I got to read a paper by a man named Kempner called A Curious Convergence Series that he wrote a bit over 100 years ago in the American Mathematical Monthly. And he starts off his paper as follows. It is well known that the series, harmonic series, diverges. The object of this note is to prove that if the denominators do not include all natural numbers 1, 2, 3, but only those which do not contain any figure 9, and there's any digit 9 in the decimal expansion, the series converges. The method of proof holds unchanged if instead of 9, any other figure 1, 2 up to 8 is excluded, but not for the figure 0. Not sure why he omitted 0, because the theorem also is true for 0. It's just you need to add a couple of lines to the proof in that case. But that's Kempner's theorem. So if you look at, if you say some digits are good and some are bad, and the ones that are bad, well, there's only one bad digit in this case, it's 9. 9 is a bad digit. So you only look at integers which, when you write them out to base 10, have no bad digit. And if you look at the sum of their reciprocals, that converges. And it easily extends to a slightly more general form. If you fix it into g greater than or equal to 2, then every positive integer has a unique g-adic representation. Pick one digit c, between 0 and g minus 1, and look at all the numbers whose g-adic representation contains no digit c. Then this harmonic series converges, and it's essentially Kempner's proof, and you'll find it in Hardy and Wright. You find it in Hardy and Wright. Okay. So what Kempner's theorem says is, if you let this A10 9, that means all the integers whose decimal expansion, whose 10-adic expansion has no 9, this Dirichlet series converges with s equals 1. So the abscisive convergence is at most 1. And as a kind of throwaway problem in my talk 2 weeks ago, I mean, I mentioned a couple of problems, but I wanted something that was just sort of simple and concrete to compute the abscisive convergence of this series. It's a series with non-negative, it's a Dirichlet series with non-negative coefficients. So there's a theorem of Landau that says that the abscisive convergence is a singularity on the real line, but what is the abscisive convergence? So right away, several people, Moshe Newman, Dick Bumby, Alex Yosevich, others, emailed me the solution, log 9 over log 10. And so I'm going to show you a simple proof of this fact, slightly more general, but it's the same proof. So in this very classical case, we're looking at g-adic expansions of positive integers. You pick a number L, between 1 and g minus 1. And for every I, every non-negative integer I, pick a subset of cardinality L of the digits from 0 to g minus 1. So in Kempner's case, g was 10, L was 1, and the subset of the digits from 0 to 9 was always just the singleton 9. So in this case, we don't have to choose the same digit or the same set of digits for each I, but we choose L digits for each I. So we're going to look at positive integers where the geodetic representation, the CI, g to the power I, none of the digits c sub I is in this set u sub I. So it's like these are the bad digits, and we're only looking at integers with good digits. We write down the abscissa of the Dirichlet series, and the theorem says that in this slightly more general case, the abscissa of convergence is exactly the log of g minus L over log g, and at the point sigma c, the Dirichlet series actually diverges. So in the case of Kempner, when g is 10, L is 1, we get log 9 over log 10. And the proof is basically a line. So, you can decompose the positive integers into intervals from g to the power m minus 1 to g to the power m minus 1. And you let a sub n be all, so a is the set of integers with no bad digits. And we let am be all the elements of the set A in this interval. So how many elements are in the set AM? Well, for each digit, you have L bad digits, so G minus L good digits. So in most cases, the number of integers in the set A in this interval is G minus L to the power M. The only time when it's slightly different is when the set U sub M minus 1. So in this interval, the geodetic representation of an integer always has exactly M digits, and the leading digits, the 1 for the power G to the M minus 1, is not 0. It's between 1 and G minus 1. So if 0 is not a bad digit, you still cannot pick it for the digit of this highest power of G in this interval. So if 0 is not in U sub M minus 1, the cardinality of set is G minus L to the M minus 1 and times G minus L minus 1. And then you take your Dirichlet series at some real number sigma, and it's summation 1 over a to the sigma, but you break it up as m going from 1 to infinity and just 1 over a to the sigma for the integers in this interval a sub m. And this finite sum, it has exactly cardinality a sub m elements. And the smallest integer in this set is g to the m minus 1. So if you make all the denominators a little bit smaller, you get something bigger, and you get this series, and you can check, it's a geometric series. So it converges if sigma is bigger than the log of g minus L over log g. So this gives one bound for the abscissa of convergence. And to get the other bound, again, you take your Dirichlet series, you write it as a series over these finite sums. And again, you can bound this from below because there are cardinality of a sub m elements in the set. And the largest element in a sub m is less than g to the m. So if I make the denominator bigger, I get something smaller. I had a lower bound for this a sub m, you get this expression. And this is greater than or equal to 1 if sigma is less than log g minus L over log g. And so that gives the proof. There's a slightly special argument you need in the case when L equals g minus 1, but it's just one additional line. So, yeah. So in the case that I brought up 2 weeks ago, when we're looking at base 10, excluding the digit 9, you get the subsistive convergence of log 9 over log 10. Now, we can extend this greatly.
So, Mel, if I could ask a question. So, correct me if I'm wrong, in that entire proof, you didn't really use anything about the set A structurally. It was just the growth conditions, right?
Correct. Correct. It's just, yeah, you were just looking, we had an estimate for, I mean, the structure of part of the set A is just this estimate for this. How many elements in the set A are in each of these intervals? And it doesn't depend on what digit you're excluding, but just how many digits you are excluding for each I.
And even if it wasn't digits that you were excluding, but choosing them some other way, as long as it has this cardinality,
correct,
it's going to be, your proof's going to go through.
Right, that's all it uses. That's all it uses. Okay, so I want to look at a more general situation. So the key part about this proof of the abscisive convergence for Kempner's theorem was that in every place I, I'm excluding exactly L digits. The particular digits don't matter. They can vary with I, but I'm throwing out, I have L bad digits for each place I. And I want to weaken that restriction. So again, we're going to look just at g-adic expansions. And now for each I, that ui be a proper subset of the interval from 0 to g minus 1, including, I mean, proper just means it's not the whole thing, but it could be empty. So ui is the set of bad digits, and we are going to have, for each I, there's some bad digits, could be none, but you can't have that every digit is bad, because if every digit were bad, you would have no numbers other than a finite set. So you have some proper subset of the digits for each I, and there's, and I want to let A, so it depends on G and it depends on this collection of U's. This is all the integers that have no bad digits in their g-adic representations. So when you write n as summation ci g to the I, the ci is not a bad digit. So it's not one of these ui's that we don't like. And we look at the Dirichlet series. And in this subject, for me at least, there's only one idea. It's very simple. I only know one way to prove a theorem. And it's the following. It's to always look at this interval from g to the m minus 1 to g to the m. You take your Dirichlet series, where A are the digits with only good, are the integers with only good digits, and you decompose it as a sum over these intervals. Right? That's all we're doing. And we make one observation that this, the integers in the set IM, it's non-empty only, that just means there's some digits you can pick at the m minus 1th place. So your bad digits, it has to be a proper subset of 0 to g minus 1. But if we're equal to if it had g minus 1 elements, all the positive integers, there's nothing in this interval IM you could pick, because the coefficient, the digit for g to the m minus 1 has to be positive. So if 1 to g minus 1 are bad digits, and if 0 is not permissible, there's nothing you can pick. So a simple condition is that if you look at all the m's where um minus 1 is not all the positive digits that are possible, your set A is finite if and only if this is finite. And if this were finite, your Dirichlet series is just a Dirichlet polynomial. It's entire, it's lovely, and there's nothing to say. So, so we only consider the case where, in fact, A is not a finite set. So this set M is infinite. So in particular, the series diverges when S is equal to 0. It converges if sigma is greater than 1. So the abscissa of convergence we know is somewhere in this unit interval. And that's what I want to find. Now, so here is a theorem. And the theorem says the following. So for every non-negative integer I, you pick a proper subset, 0 of the digits, so that first of all, you are not picking all the positive digits, all but finally many times. And second, so this is the key thing.
Go back one page.
Back one page, okay.
I don't think you want to say just that M being finite. The only problem is when you get 1 to G minus 1 excluded when, on a cofinite set. You can still have a set where infinite many digits are 0. It will still be an infinite
yeah.
set of.
Yeah, no, that's right. I changed this. I was getting these, doing these slides a few minutes before 2:30 today, because I was trying to find a slightly simpler form. But there is some condition like this, and if I wrote it down wrong, I'll correct it at some point. But that's the idea. I mean, you don't want to have a finite set of integers, because then you just have a Dirichlet polynomial. Thank you. Okay. So this is the condition I need on these bad sets of integers, bad sets of digits. If you look at the first m sets of digits, so for I going from 0 to m minus 1, your sets u sub I have how many elements? Well, some number between 0 and g minus 1. So for each k, I want some uniformity in how many sets there are of size k. Namely, if you look at the first m sets of bad digits, the number of size k has a certain density. It's like alpha k times m plus some little remainder, and the remainder has to be such that it's epsilon k of m over m goes to 0. So in the case of Kempner's theorem, where every set had size L, then you would have had alpha L is equal to 1, epsilon is 0, epsilon k is always 0, the other alpha k's were equal to 0. So what I want is that if I look at the first m sets of these excluded digits, the number of size k, there's a certain fixed proportion of them. So that's my condition. And so again, I let A be the set of all positive integers with no bad digits. That means when you write n to base g, if you write it as ci g to the I, with the leading digit cm minus 1 different from 0, and none of the ci is a bad digit, that's my set A. And the theorem says that my Dirichlet series has exactly this abscissa of convergence. That's the theorem. So that means for sigma greater than this number, the Dirichlet series converges. For sigma less than this number, the Dirichlet series diverges. And in this case, I don't know what happens at the abscissa of convergence. We know it's a singularity, but the series could still converge. Yeah, that's the problem. Now, if I am slightly more restrictive about the uniformity in the distribution of the sizes of these sets u sub I of bad digits, I can get a slightly more precise theorem. So this is the second result. You take for every I a set of bad digits u sub I. Forget this, that's, to be corrected. But if you look at, so in this case, I want something stronger that if you look at the number of k, the number of i's from 0 to m minus 1, where there are exactly, and I count the number of sets u sub I, or the number of sets of bad digits of cardinality exactly k, it's alpha km plus a little remainder or error, and this is smaller than what is, the epsilon k of m goes to 0. So this just means you have more uniformity in the distribution of the sets. And in that case, I take the set of integers, positive integers, with only good digits, and
Excuse me, there's something I'm missing here.
okay.
You say, back up again, you're saying that k goes to 0, right? But isn't it a counting function? I mean, we have a cardinality, and I'm missing something here. Just a second. Alpha km. No, I'm still not getting it. We haven't. Can EK go? Basically, are you sure that EK can go to 0?
Well,
I'm sorry.
what you're saying is that from some point on, these EKs have to be equal to 0.
Okay. Okay, so it's, in other words, the alpha k's are rational, and yeah, all right. Okay, yeah.
Okay. What I was trying to do was find a condition where I would know whether or not the series actually did converge at the abscissa of convergence. That's all. I was just trying to ask myself, under what conditions could I actually determine convergence or divergence at this point? And so with that condition, even though whatever it is, you do get divergence. That was the whole point. Okay. So yeah, there's some preprint I just put on archive that has the proof of this if anyone's interested. But several people, Moshe Newman and some others, said that there is something called an automatic Dirichlet series. Actually got an email from a guy in Australia who said, I saw your preprint or something, or whatever, and you have an automatic Dirichlet series. So, so the word evidently, I didn't realize this, was applied to certain sequences of integers by Jean-Marc Desouliers. The subject preceded him, but I think the nomenclature, the terminology is due to him. And years ago, he spoke about this in our number theory seminar. But I've completely forgotten everything he said, and I also completely forgot what was an automatic sequence. So I had to look it up. And so there is something called an automatic sequence. It's and there are a variety of equivalent definitions. But one basic thing seems to be, you have a sequence of integers, v1, v2, v3, and you want to know, how do you compute or determine what is the digit, what is the nth term of the sequence? So you pick your base g, you write n, you represent n g-adically. You look at the digits, and somehow in some algorithmic way from the digits, you compute v sub n.
Yeah,
So,
the key word here is a finite state machine. The computation can be done with no memory. That's the heart of the issue.
right.
It's not just algorithmic. It's a sort of low complexity algorithm.
Right, and I avoided saying that because even though I know the words, I don't have any kind of emotional connection to what the words mean. So, but yes, I mean, and Yes. I mean, if you go to Wikipedia or I guess Jeffrey Shallot and one of the three authors, maybe Alouche, actually wrote a book on automatic sequences.
Alice, yes, yes. And, computer scientists will have, anybody who studied a computer science course will have met the concept. So it's you may not have that emotional connection to it, but the younger generation doesn't have a choice.
Right. Well, yes. I mean, I can barely, actually inadequately figure out how to use Zoom. But okay, anyway. So take one of these sequences we've been talking about, the positive integers with missing digits. And so if you write down the characteristic function of the set A, then the Dirichlet series we're looking at, summation 1 over a to the s, is summation chi sub a of n over n to the s, where this is the characteristic function. So an automatic Dirichlet series is a Dirichlet series where the coefficients, the numerators in these fractions, something over n to the s, form an automatic sequence. So, and in this paper of Alouche, Mendes, France, and Priere, there are many beautiful properties of such Dirichlet series. They have meromorphic continuations. Their poles satisfy certain properties. There are statements you can make about the logarithmic density of the values of the automatic sequence and so forth. So I have no idea whether this is, or how this is sort of relevant to the kinds of results I've been talking about, which were just simply trying to figure out the convergence properties of these series. But this is one thing that I wanted to mention.
I couldn't figure out any way to make the results in that paper help you actually find the abscissa of convergence. I spent an hour or two, couldn't see that it was relevant.
Right. I mean, it might say something about the, so you have the set of integers, positive integers. It may or may not have an asymptotic density, or what they call, what some people call a natural density. But it may be, you can say something about the logarithmic density of the sequence, because that is one of the results about, there are things in these various papers about the logarithmic density of automatic sequences. Okay.
Yes.
I think, though, that in this case, the logarithmic density is just 0. So, it isn't very, their paper isn't very helpful from that point of view.
Yeah. Okay. Now, Hausdorff dimension. So, I mean, how would someone think that for the set of integers that come out of Kempner's theorem, if you look at the integers that have no 9 in their decimal expansions, that the abscissa of convergence should be log 9 over log 10. So one way to think about this, perhaps, is if you look at the related problem for sets of real numbers. Say you look at the set of, like the real numbers between 0 and 1, which you write as infinite decimal expansions, and you look at basically the Cantor sets. So if you look at the Cantor set of numbers with no 9 in the decimal expansion, that has Hausdorff dimension log 9 over log 10. Now, Alex Yosevich, who thinks about Hausdorff dimension quite a bit, sent me the following email, which I will quote directly. Because he also understood that for the Kempner problem, the abscissa of convergence for the Dirichlet series, for the set of integers, excuse me, was log 9 over log 10. So he said, you are trying to build a Cantor type set as follows. At the first stage, you divide the unit interval into n equal pieces. You then remove one of these pieces at random. You then divide each of the remaining n minus 1 pieces into n pieces each. And once again, remove, I had put this in a probabilistic form when I was writing to him about this. Remove one piece at random from each and so on. You then take the intersection of various stages. If this is what you mean, he's saying to me that the Hausdorff dimension of this set is log n minus 1 over log n. You choose k intervals at random from n just as easily, and you will end up with a set of dimension log k over log n. And what I believe, maybe some people here, but certainly Alex Yosevich understands, is some kind of almost algorithmic way to move back and forth between sets of positive integers and these sets of real numbers. So I asked him actually if he would give a talk about this at some point, to which he gave his usual response, which is, sure, maybe, yeah, maybe. So, so we'll see. But it is kind of, well, just interesting. All right. Well, that is in fact all I wanted to say. How this problem I had posed sort of on a lark 2 weeks ago about the abscisive convergence for Kempner's theorem can actually be calculated and generalized a tiny bit. And how there does seem to be some connection to Hausdorff dimension, which, you know, you can sort of see physically in some sense, but I don't understand. And also this question of whether there's something with automatic Dirichlet series that, you know, may be relevant to this. In any case, it's not. Well, who knows? Anyway, that's the whole story. I thank you all.
Many thanks.
Thank you.
If I can figure out how to shut this down and get back to my normal screen, let's see. Stop share. I'll try that. Ah, okay.
You should get in touch with Jerry Myerson.
Because
He probably knows
on
the
the
automatic-
Hausdorff dimension issue.
the automatic sequences.
Uh-huh. Is he still in Australia?
I think so.
All right. Oh, I have a general question for the world, unrelated to number theory in every way. I've asked a couple people this, but I can't get. So at Lehman, we offer a course, an undergraduate course in partial differential equations. Students are not required to have taken ordinary differential equations or linear algebra. In fact, the only prerequisite is 3 semesters of calculus. You know, that's it. Does there exist a textbook in PDE that don't assume you know anything about ODE or anything else? Is it possible? How do you teach a course like this? If anyone, no, I mean, if anyone can think of, I'm happy to get an email. I'm really curious because it's not that I will be teaching such a course. It is that I am currently teaching such a course. And after giving a couple of weeks on a couple of weeks of lectures, first 2 weeks basically, some very elementary PDE stuff, I realized I had to like take off a month and do some ordinary differential equations because they had never done it. And if you reduce a PDE to an ODE, there's not much point if you can't do the ODE. So, and I truly have not been able to find anything that I could be using as a book other than scrounging around various bits and pieces. But And I can't
But
imagine.
where's the sense? I mean, it sounds like trying to teach advanced calculus without basic calculus. I am. Why wasn't it required as a previous course?
The answer is I don't know. I would guess it's because someone thought we should have a course in PDE. We don't have a large number of math majors. If you required ODE, then you probably wouldn't get enough students to offer the class. Half of this, so I'm offering the class. There are only like 13 or 14 students. 3 or 4 of them are actually physics majors, but which is fine. But
so whether or not they've taken a course in ordinary differential equations, they know about ordinary differential equations.
Right, but that's 3 or 4 out of the 15. So, and you can't just teach to the 3 or 4.
Having taken a course does not mean they remember anything.
Right. Well, yeah, that's also true.
I had a course called Introduction to Applied Math. And at the first meeting, I gave a quiz 0, which was the differential equation dy dx equals constant times y.
You're really pushing it.
And almost no one knew what the solution was.
Well, the one time I think I was on sabbatical and spent a semester at Rutgers, I taught a section of calculus, either maybe 3rd semester calculus. I thought the students were really good. I mean,
Of course. It's Rutgers.
you just said your students didn't know how to solve, y prime equals k times y.
Look, Mel, for whatever it is worth, you still deal with very advanced students, but I had a horrible experience. So if you want to give them something which they can take away, I would just teach them a few tricks, like, for example, separation of variables. And for elliptic things and others, but where you can really show how you can solve it in series, and then I would do with them some operational calculus.
Mm-hmm.
Because this they will learn, and they would be able, to do some kind of Laplace transform. Because otherwise, teaching a full-blown PDE course without multidimensional calculus, linear algebra, and ODE is belong to the science fiction.
Right. Yeah, exactly. That's what I've discovered. So I'd actually picked a book that I thought might be accessible. So I thought I'd pick a book that was like PDE for scientists and engineers. So they would at least learn applications and models and so forth, but even that seemed a bit too, anyway, that's just our strange situation. All right, what else is going on? I don't even have the schedule in front of me. We have 3 or 4 speakers in the next month or so. Here, see if I can find it. Oh, Jim Sowers next week. Excellent. Matthias Beck the week after that. Emily Bailey 2 weeks after that. Good. Well, everyone's so quiet.
If you wish, I can contribute a question which seems hopeless, but is related to what you've been talking about.
Okay.
So you've been looking at, I mean, instead of considering sub-series of the harmonic series, sub-series of the Dirichlet series that define the zeta function, right? Instead of summing 1 over n to the x for all n, you sum over some subset.
Yep.
So for which subsets can the resulting function be continued to a meromorphic function in the whole plane? So, I mean, there are any number, you can come up with any number of obvious special cases. The automatic family you just mentioned is a very large family. There are lots of others. My conjecture is that there are uncountably many such, but I don't know that anyone's ever actually proven that.
So what are classical examples of such series that don't extend meromorphically to the plane?
I think that if you take any really sparse set, you know, like let's say you take 1 over n factorial to the x, I think that's going to have a natural boundary. I think the usual proofs that are used for power series that have natural boundaries will work for this too. Okay, or I don't know. You know, some very sparse sets you can show that there's going to be a natural boundary, and I think that there's a sort of probabilistic argument that shows that in some sense you usually get a natural boundary. But I can't actually make that sort of argument work. I'm not experienced enough at using it.
Right. So if you take a Dirichlet character, you know, chi of n, is that an automatic sequence?
Yes. Every periodic sequence is automatic.
Right. So automatic sequences always have a finite range, right? This I know. And it doesn't matter whether the range is complex or whatever. Okay. So what's a nice example of a sequence that is not automatic?
The sequence of squares.
And that's an example where you would get, by the way, meromorphic continuation, because that would be just zeta of 2x.
Right. No, but I mean a sequence which has finite range. So the squares is infinite range, so it can't be automatic.
No, the range is the range. We're just looking at a characteristic function. The range is 0 and 1.
Okay.
Here's something where we're taking coefficients, not a characteristic function, and the same techniques would apply. You can show that the Dirichlet series has a meromorphic continuation. Look at the Kalkin-Wilf sequence: 1, 1, 2, 1, 3, 2, 3, 1 for enumerating the rationals. That sequence is very closely related to automatic sequences, but it isn't an automatic sequence. It's covered in the Alush and Shalit book. And if you take those numbers as coefficients for a Dirichlet series, you do get something with a meromorphic continuation. The paper by Alush and Cohen.
So why do people get so excited about automatic sequences?
They show up a lot.
Well, why was I able to have such a satisfying mathematical life, not knowing what an automatic sequence is?
Well, you see, you were using them without knowing what they were, right? I mean,
I know.
forbidden digits
It's like
is an example.
I just learned I was speaking prose.
Yes, exactly. Or how about the 2 or more sequence? Or how about, I mean, automatic sequences, sometimes they're sort of thought of like quasi-crystals. They have, you know, they're a sort of low complexity structure, which isn't periodic or which isn't necessarily periodic. I mean, they're interesting for a lot of purposes. Obviously, you can do a lot of math about that.
Right. So evidently, there was some computer science guy named Cobham, C-O-B-H-A-M, who
He's
invented
more than a computer science man. He did work on logic. He showed that the theory of elementary theory of finite groups isn't decidable. He did a lot of interesting things. Yes, he's not just computer science.
But on MathSciNet, he only has something like 8 publications.
Well, but they are very weighty publications.
He founded a few fields without publishing a lot in them.
Ah,
But by the way, he is also a very good hardware designer. He did a lot of hardware design at IBM. He worked at IBM for a very long time.
uh-huh. Because he wrote one paper on the subject, which is referred to hundreds of times, and he has like a funny name for the sequences he's talking about.
Tag sequences.
Excuse me? Yeah, uniform tag sequences. That was the title of his paper. Ay, ay, ay. All right. James, we look forward to your talk next week.
I'm looking forward to it as well. Thanks, Mal.
Okay. I'm going to go off to the whatever that rotating number theory seminar we have between Columbia and the Grad Center in Courant.
Yeah, but that's at 5, isn't it?
So I'm right. So it's maybe 5:15 to 5. It's early because there's no like coffee and stuff. But I want to see whether I can get into the session for graduate students that they have at 4 o'clock, where they explain, where faculty generally are not allowed, and whoever is the speaker is supposed to explain to the graduate students what the hell he's going to talk about. I remember one semester I was on sabbatical at Princeton at the university and not at the institute. And whenever they had a colloquium talk, they had a colloquium once a week. They also had the same thing where an hour before the actual talk, the colloquium speaker would have a session with graduate students. Only the way they worked, it was in the tea room in Fine Hall, and there weren't necessarily many graduate students, but all the faculty went to hear what it was that they would explain to graduate students. So all the great names that were there, because it was typically not something, in their field, and they wanted to understand it. So they knew that the colloquium would be incomprehensible. So I'm curious to see whether the Zoom login will let me in at 4 o'clock.
They say you have to get a special permission to get a special password.
Yeah, last week I didn't try last week, and so yeah, I'll see. Whatever. All right.
Can I say something, Mal?
Yes.
So I reached out to Madeline Brandt, if you remember, who did the stuff about packing polynomials, and we're doing a write-up together about the classification of packing polynomials on rational, or all sectors, really, as we know. So when we put that up, we wanted to cross-reference it with the other paper, the one that I send you that
For the
was
proceeding.
basically my talk at Kant.
Right.
So I just wanted to hear if there are any issues, if I can take that article and put it on archive on the same day as the other one and edit it and cross-reference the two.
Oh yeah, of
Is
course.
everything
I mean, you
fair
can.
game?
I mean, you can put it on anytime. You can put it on right now, and you could put it on
Okay.
a year ago.
Yeah. Oh, so I just thought I'd wait because the two articles are going to reference each other. So I figured it would be more convenient to have them both up at the same time.
Doesn't matter. I mean, if your singly authored paper is ready, I would just put it up. And, you can just put, if it refers to the other paper, just put in the references as, to appear or in preparation.
Okay, and then you just edit.
You can
You
go
just
back
edit
into
it
archive
later?
at any time and change your paper. I mean, they actually hope, they say, they want people to go back and re-edit their papers if, either to correct a typo or whatever, because they want their papers to be as correct and up to date as possible.
Okay.
Yes,
Okay,
I
that
wouldn't
sounds
wait
good.
for that.
Yeah.
Now, if you're doing it for the first time, they might require that someone certify your bona fides, says, that you're
Any
not
volunteers?
you're not. I mean, I mean, you can put me down as someone they can contact. It's I guess they're afraid of the possibility that someone has a paper where the title was Packing Polynomials, but it's explaining the QAnon conspiracy and how packing polynomials are some pedophile group in Washington, out of a pizza parlor in Washington, D.C., or God knows what.
Well,
So,
I think that it doesn't matter what you write. You can read whatever you want into it. And I use capital Q quite a lot.
right, well, just so, actually, yeah, well, that's fine, but it's just the anon after it is that might flag someone's attention.
Yeah, but what does that superscript 2 really mean?
Who knows? Who knows?
Could be anything. Yeah.
I've had
So it's also possible that I'll volunteer for a talk sometime in the future.
good. Sooner the better. Love to hear you.
All right.
All right, everybody. I'll see you around next week. Stay well.
Be well.
Bye, everyone.
Bye.
Bye-bye.